Did everybody get the email I sent you that has the license registration code for WMS? Okay. So you can use that and activate it and get the full functionality that we're going to be using. We'll begin talking about this software after spring break. I may spend a few minutes giving you kind of a qualitative demo between now and Friday, just depending on how some timing works out, but you won't actually need to use it until after spring break. Speaking of after spring break, the next homework assignment that's on your plate isn't due until the Monday after spring break, so you've got 2 weeks to work on this next one, the unit hydrograph and time of concentration. And that's what we're going to talk about today is an application of the unit hydrograph ideas that are specifically applicable to watersheds that we're modeling with the NRCS method. So rather than time of concentration just for the shallow sheet flow, this time of concentration that we're going to be calculating is time of concentration for an entire watershed. And remember when we were doing calculations before with the Kirby method, Kerr pitch, kinematic wave, when we were doing that time of concentration, those were relatively short distances. We were just thinking about water flowing over a surface for about 100 meters or so. But we can also think about time of concentration in the context of an entire watershed that's relatively large. So that's what we're going to be getting into today. Are there any announcement questions you'd like to ask before we move in? All right. Our book has this figure, and I wanted to point out kind of the basis for this figure is a triangle. And you can see here with the dashed lines, it's a triangle that on the as the water flow rate is increasing, has a relatively short base and a relatively longer base as the flow rate is decreasing and a watershed is draining. And that's kind of the basis for this unit hydrograph, is it's similar in concept to the Snyder method. And remember, the difference between an actual unit hydrograph and the Snyder unit hydrograph is that the Snyder method is synthesized for a watershed that you don't actually have physical measurements for. All you've got, well, you have physical measurements of the watershed, but you don't have direct observation of runoff. So you may know a watershed's slope, you may know its curve number and its area, and those are all measurable things. But what you don't have for watersheds that you're going to use this method on is you don't have a stream gauge where you're specifically measuring what the flow rate is, and you don't have a rain gauge that's specifically measuring what kind of a storm event caused that runoff. So this is a synthetic approach, where of course it's better to apply a measured unit hydrograph, but it's going to be pretty rare that you have a calibrated unit hydrograph for a watershed you're interested in. So instead, we look at regionally developed hydrographs and kind of combine them all together with typical characteristic behavior. And so that's what this is this is just an approach that says if you look at enough watersheds, it seems like it takes longer for them to drain than it did for you to achieve the peak flow rate. So if you look here at the T sub P, that's the time to peak from the initiation of the event until you have the highest flow rate, T sub P. This receding time, T sub R, is 1.67 times as long. And so they've also, rather than just making a strict triangular distribution, they said, well, we can generally count on the fact that it doesn't instantaneously start flowing and increase linearly. So they had kind of this tapered, gradual lead-in where there's a curve rather than the triangle, but it's still, the area under the curve is mostly triangular. And so then the same thing on the downswing as the flow rate is receding. Rather than going linearly from the peak to a hard zero, they kind of curved it out a little bit and extended the total period that the discharge is decreasing. So a couple of other definitions is the duration of the rainfall is the width of this gray bar. So this gray bar is meant to be just a single pulse of rainfall that is our unit hydrograph. So for a unit of excess rainfall. So this SCS unit hydrograph presumes that we've already done the NRCS method to find out what is P sub E coming out of P. And remember the NRCS method, the differentiation there, let me write it on the board. P sub E, the rainfall excess, is reduced by the watershed's capacity for storage. So P sub E is P minus 0.2 S squared divided by P plus 0.8 S. So from the curved number of the watershed we get S. P is the depth of precipitation, and P sub E is going to be the rainfall excess. Sometimes we know that as the runoff. So this SCS unit hydrograph method says we know the depth of excess rainfall, and we've gotten it from here. And so then we can develop this curve that's based on a unit of rainfall excess, and the times are also scaled. So the height of the curve is scaled. If you look at the units here for the vertical axis, it's saying Q to QP, or lowercase q to QP, or capital Q to Q, Q naught to Q. And that's basically meaning if you know the peak runoff in terms of CFS, then you would multiply the flow rate ratio at any time by that total Q sub P, and that would give you the runoff in CFS at any particular time. Or if you just know the depth of runoff to the total depth of runoff, then you can likewise scale it, and your vertical height of the hydrograph will be scaled based on the 1 unit of rainfall excess. So the horizontal axis is also scaled. Everything's based on the time to peak, and so 1 occurs at the highest flow rate, and this doesn't have units yet. It's unitless for now, but if we calculate the time to peak, then we can prepare a hydrograph that tells us in hours how long it is until every point on this curve. And that's what we're going to do with the example that we'll work through today. The advantage of using this approach is that it can be applied to any watershed that you have the SCS data for. And the data that we need to calculate the response of a watershed to a storm is going to be the hydraulic length. So that is a measure of the largest stream in the watershed. The S, the maximum retention that comes from the curve number. And remember, curve number is a reflection of both the soil type and the land use. And so we can go to tables, or we can go to GIS data and figure out within the watershed what's the composite curve number, and from that get the storage. And then we also need to know the slope, because the steeper the watershed is, the more quickly it's going to arrive at the peak. And so we put the slope into this empirical equation as a percent, which is a little bit different from normally how slope is expressed as a decimal. Here we leave it as a percent. So if it's 2%, you'd put the number 2 in for y. So once we know the lag time, which is measuring from the middle of the rainfall event to the peak, then there are these extrapolations that allow us to know, if you know the lag, what's the time of concentration, and if you know the lag, you can also calculate the width of the time to peak, the width of this receding base, and it's a pretty simple way of transitioning the NRCS method, which just gave us depth, into something that gives us flow rate and time. Because remember, the units here for P sub E is just inches, where what we really want to know is how many CFS needs to go through the culvert pipe, or what CFS will be going through a stream channel. And so this unit hydrograph allows us to tie the two things together. Now, there are a couple of embedded assumptions when we calculate the peak discharge. And one of them is what kind of a peaking factor applies for the watershed that we're dealing with. And you can see this factor 484 is used in here. It's known as the peaking factor for typical SCS characteristics. And if you have a really flat watershed that is rural and has an abnormally high potential for infiltration and slow time to peak, then you could bring that peaking factor down as low as 100. And if you have a really steep urban watershed where it's going to be even flashier than might be predicted by the base assumptions of this equation, then you could increase the peaking factor. What we'll do is we'll just go with this base typical SCS, but you know, here in West Virginia we kind of have unusually steep slopes, but we also have relatively high quantities of vegetation in the watersheds. And so it's hard to know whether you'd want to deviate upwards or downwards for one particular watershed unless you have a way to calibrate it after the fact. So that's why we'll just stick with this typical peaking factor of 484. So if you look at this Q sub P formula, what you're going to get out of this is you're going to find out the cubic feet per second for a watershed, where you're putting in the area in miles, and then you put in the rainfall excess in inches. And so let's try this out with an example. This example is slightly different from what appears in the notes. I've made some adjustments just so that we can start from the very beginning, and so you can see from start to finish how you could apply the SCS unit hydrograph method. What I'm going to do is allow you to calculate these points 1, 2, and 3, and then together as a group what we'll do is we'll address how we would find the runoff hydrograph, knowing that this is in Huntington and we want to get the storm data out of the precipitation data frequency server. Okay, so just substituting into these formulas, you can see here for the time of concentration, I've given you the formula for the lag time, and from that you get the time of concentration. And all of the values are in the units that are needed. So for example, L, you should put in the, you need to convert that to feet. So I've given you the hydraulic length in miles. You need to convert that into feet. So it's, is it 5280 feet per mile? I'm blanking for a minute, but I think that's it. 5280. I see some heads shaking, nodding, that is. Yeah, so you'll need length in feet, S is inches, and so here is the formula for S, and you've got curve number up at the top, and then the slope stays as a percent. Excuse me. All right, so let me pause and give you some time to do these calculations, and then we'll do the application together. All right, so in calculating the time of concentration, we put in the hydraulic length, the S value that comes from having known the curve number, and then the watershed slope. So that tells us the lag time is 0.656. And let's just go back to the figure and refresh our memory on what that's talking about. So T sub L is from the midpoint of the excess rainfall to the peak. So 0.656 hours. And so therefore the time of concentration is 5/3 of that, 1.093 hours. Time to peak is 2/3 of the time to concentration, so 0.729 hours. And then that's what's used in this formula where we're trying to determine how many CFS is going to be the peak flow rate per inch of rainfall excess. So when this is talking about per inch, It's not per inch of precipitation, it's per inch of rainfall excess. Okay, so it'd be 1992 CFS per inch. Now, that tells us how high this peak is, and it also tells us, it defines how long it is from time zero to this time to peak. So basically what we've said is from the beginning of the storm to when we'll see the highest flow rate is 0.729 hours. And the height of this hydrograph is going to be 1,992 CFS for each inch of rainfall excess. Now, we've got that curve digitized. Here's that digitized curve where, rather than having to just look at the actual curvature of it, here are the values. And I've loaded this onto Blackboard. If you've got your computer, what we're going to do next is we're going to take this digitized unit hydrograph and turn it into an actual hydrograph. So the second part of this example says this watershed is in Huntington, and we want to see for the depth of precipitation that's associated with the 2-year storm, 24-hour duration. So let's go to the precipitation data frequency server. All right, so we're clicking on West Virginia for the map. And here's the cursor. Maybe I need to zoom in a little bit to see Huntington. All right, so I'm going to drop the cursor on Huntington. Although it won't change much depending on what part of Huntington. If we're talking about a 3-mile watershed, it's probably not going to be in the flat part. So let's just put it in the South Hills a little bit. All right, so here is our precipitation, and it's set to depth right now, which is what we need. So the 12-hour duration, 2-year return period. So 2.64 inches is the rainfall. So P, let me erase this stuff that's on the whiteboard already. So precipitation data frequency server has given us the depth we're going to use for P, and we'll use the NRCS method to find P sub E. So P is 2.64 inches. And what we already calculated was, we know S is 1.63 inches. Did we calculate that? Yeah, in the first step. Let's go back. Yeah, we used S here, so we already know that S is 1.63 inches. And we're going to use the NRCS method to tell us how much precipitation excess there is going to be for this storm. So just to have it on screen as I also write it on the board, the NRCS method that we're using is this one. So P sub E is P minus 0.2 S squared divided by P plus 0.8 S. Okay, so we know P, we know S. Find the P sub E, and then that's what we're going to use with this Excel file that I put on the Blackboard. So let me give you a moment to calculate the rainfall excess. Okay, so did you get 1.36 inches? All right. So there's a storm of 2.64 inches. What's going to come out of the watershed is 1.36 inches. Now what we want to know is how does that translate to the flow rate versus time? So the actual hydrograph is what we're going to try and generate. So let me download. Are there any questions so far, by the way? If not, let me go to Blackboard and get that same file as a starting point, just so you don't have to type it in, because all it takes is one accidental keystroke in the wrong spot and you got the wrong hydrograph. Down here at the bottom, the XY data. All right, so we've got the time ratios where this is just some time relative to the peak by which we're defining the discharge ratio. So by definition, the peak discharge occurs at the time to peak. And then all the rest of this is just trying to tell us the shape of this curve. Like how quickly does it taper upward to the time to peak, trying to get that slowing of runoff growth near the peak, and then it quickly descends, and then this point of inflection is when it's no longer accelerating in the rate of runoff decrease and it's starting to slow the rate of drainage. So we've got that here. Let's put at the top, first of all, the time to peak that we've enable editing, of course. Okay, so let's define the time to peak, and that was in hours, what we calculated so far. Let's define the Q sub P, which was, when we calculated it, the CFS of runoff per inch of precipitation excess. And let's also have a cell where we define what is the precipitation excess. Okay, so what we had calculated was it was 0.729 hours for the time to peak, and we determined that it's 1992 CFS per inch of rainfall excess. And then just now on the board, we said it was 1.36 inches of rainfall excess. We used the NRCS method to determine that. So just think about, like, what do we know about this watershed? We know its curve number, its area, the length of its biggest stream, slope. Those are the physical characteristics that we know about. And then we're also predicting how it's going to respond for a certain storm. Okay, so what this method does now, we're going to have a column that we have time in hours, and then we're going to have a column with discharge, and that is going to be CFS. So the time in hours will be, we're going to do a formula here where we multiply the time ratio by the time to peak. Because right now this is unitless, but the time to peak will tie it all together with units of hours. Okay, so it is equals the time ratio multiplied by the time to peak, and I'll anchor the reference to the time to peak with the F4 button, and that way I can drag that cell down, and it's always looking in E1. So let me drag that down through all of the rows that we have some entry for. So up until 3.645 hours after the storm begins is what we're predicting. And then for the discharge ratio, is a little tricky, because this is the Q sub P per inch of rainfall excess, but we have 1.36 inches of rainfall excess. So each one of these cells will be multiplied by that and by that, because this is per inch, but we have more than an inch. We've got 1.36 inches. So the formula is going to be the discharge ratio multiplied by Q sub P, anchoring the reference with the F4 button, times this cell where we've got the precipitation excess that we're actually going to see for this 2-year storm event. Because we're not seeing that unit of rainfall excess, we're seeing more than a unit of rainfall excess. And so the discharge is going to be higher than the peak flow of 1992 CFS. All right. So now we can drag this down through all of the rows that we have a data entry for, and what we'll see is that the highest flow rate does occur at the time to peak. If it didn't, boy, that would tell us something was wrong. But we have that highest discharge at the time to peak. Okay, so check. And then the magnitude of it is 1.36 times what this predicted flow rate maximum was, because we had more than the inch of rainfall excess. Okay, so the last part of this is for us to make a meaningful figure. So we can go here into insert, and let's create an XY chart that has the nice smooth lines, and we don't need the underlying data points graph necessarily. So I'm going to select the data and have for the X values time, and for the Y values we'll put the flow rate. And that shape does look so far pretty close to what we have in this figure. The shape of it, it's taking a long time to drain. Up to 5 times the time to peak is what we're keeping track of it. Now, if this was predicting like the flow rate through a river that had some flow in it even before the storm, then we'd need to add the base flow on top of all of this. So, if there was 10 or 20 CFS going through this stream even before the rainfall event, we'd need to scale everything up vertically by that amount. So it's not necessarily saying that the watershed's going to go down to 0, but just the contribution of this particular storm will drain down to 0 after 5 times the time to peak. Okay, so let's put in some axis titles. On the horizontal axis, that should be time in hours. And the vertical axis will be discharge in CFS. And then we could label this as Huntington watershed, 3 miles square, CN 86, 2-year storm. Now, there's one kind of simplifying aspect of this example I wanted to bring to your attention, and that is, look at the duration of the storm. So T sub R is how long the storm lasts. And it should be less than the time to peak. And ideally, it should be a fraction of the time to peak. And so what was our time to peak? Our time to peak was 0.729 hours. So what that means is it's best if what you do with this method is you have a rainfall hydrograph that's broken up into pieces with a duration that's less than the time to peak. So for our case, if we had rainfall data that was maybe every 10 minutes, how much precipitation is there, then that would be good. We would want to apply this method over and over and over, lots of different times, where each time step was looking at just how much precipitation was there in this 10-minute time frame. In the example, what we did was we took the entire 24 hours of storm and lumped it together. So we took this, the precipitation data frequency server said 2.64 inches. So I just took that depth as a big all-at-once amount. But what we're going to see when we apply this in WMS is WMS breaks the 24-hour storm into those little tiny slices of precipitation. And it does it with the 24-hour distribution. Let's go back to when we were talking about temporal distribution of precipitation. What WMS will do, where's that distribution? I know we've seen it. Getting close. It's been a long semester. There it is. This temporal distribution. So the 2.64 inches that we just talked about, here in West Virginia we are type 2 storms. So if it's 2.64 inches in a day, then this tells us how much of the precipitation has occurred up until what point during the day. So WMS will use this distribution and it will step through a simulation where every 6 minutes, 10 minutes, 15 minutes, whatever you specify, what it'll do is it'll just look at the tiny little bit of rainfall that's happened during that time, and then it's going to send it through the calculations of how much precipitation excess is there for just that 15 minutes worth of rainfall. And then therefore, it will stack together a bunch of successive unit hydrographs and make one combined runoff hydrograph from that step-by-step approach. So I wanted to let you know that that's what it's going to be doing in the background, but it's all derived from the same idea of a unit hydrograph where we don't necessarily have a measured outflow from a watershed, but we do have physical things that we can use to predict what the runoff hydrograph might look like. We've got the area of the watershed, we know the curve number and the physical characteristics like the length of the largest stream and so on. So yeah, that's basically it. That is the unit hydrograph and how you could calculate the time of concentration for an entire watershed. Any questions about the example that we went through today? All right, well, remember that homework 8 is due in a couple weeks, and also you should download and install WMS. That's it for today. I'll see you on Wednesday.